Okay, assalamu alaikum and welcome back to our part 2. Today we are going to talk about the analog to digital converter in the ATmega16. Previously we have talked about the analog to digital converters in general, and we have said that we have a few things that can control our analog to digital converter. Basically the sampling frequency and the number of bits that are used for quantization. So if we have the analog to digital converter in the ATmega16, which is a 10-bit analog to digital converter. 10-bit analog to digital converter means what? Means we have n equal to 10. This will give us 2 to the power 10 different values, which is 1024, and we have 8 different sources. Type 8 different input channels does not mean that we can use them all together. What we have is one analog to digital converter connected to 8 different sources. So we need to choose from which source to take at each time. Okay, this is what we mean when we have 8 input channels for the analog to digital converter. However, it will perform only one channel at a time. This is stated over here. If the default reference voltage V reference is equal to 5 volt, then the step size will equal to V 5 volts over 1024, which is 4.88 millivolt, giving us an accuracy of around 9.76 millivolts. So to get the perspective, when I say 4.88 millivolts, this is equal to 0.00488. This is how small the voltage we are talking about is. It takes around 13 cycles because it's using the successive approximator method. Now, as you see, when I said 8 input channels, because it is connected to port A, and you can see here that port A is basically 8 bits, and we have ADC0, ADC1, ADC2, ADC3, ADC4, ADC5, ADC6, and ADC7. We have an external V reference if we don't want to use the actual reference voltage, and we have a power supply to the analog to digital and port A. Okay, if we are using the analog to digital converter, we need to give it its separate supply, and we have a difference reference voltage if we do not want to use the actual built-in analog to digital converter. So this is the circuit we are concerned about. If you see over here, we have a multiplexer, an 8x1 multiplexer. It will choose between 8 of the input pins. Here we have the analog to digital converter mux to select which input. We are going to talk about it. We have the analog to digital converter control status register A to configure the analog to digital converter, similar to what we had in the serial port. And here we have the analog to digital converter high and low, which will produce the output. Now remember, the output is 10 bits, and the outputs is 10 bits, and our microcontroller is 8. Our microcontroller is 8 bits. So in order to have all these values in the microcontroller, we will need 2 registers. Okay, we will need 2 registers, the low register and the high register, and it depends how we are going to deal with that based on what we are going to see right now. Now, the ADC mux. The ADC mux, remember, we have 8 different inputs, so we need 3 bits, but as you can see here, we have 5 different inputs for the multiplexer, and I will tell you why. Then we need to see whether we are going to use left adjustment or right adjustment, and we want to use the reference bits. What is the reference voltage that we are going to use? For the reference voltage, we have 3 different choices. For the analog, input voltage can be selected from different pins. Differential input can custom the gain factor. The analog to digital left adjustment register will either be 0 or 1 to show you how we are going to adjust the bits. So first of all, let's talk about the reference voltage, which is these two bits over here. How are we going to connect these voltages? Now these two reference voltages are basically either 0, 0 for A reference, internal V reference is turned off. If I want to use this pin as my reference voltage, then I'm going to put these two bits as 0, 0. If I want to use the A VCC with external capacitor as A reference pin, so if I want to use, if I want to use this one as my external value, also I can use it, and to use it I will going to choose 0, 1. Then if I want to use 1, 1, again 0, 1 is reserved. If I want to use the 1, 1, this means the internal 2.56 voltage reference with external capacitor at A reference. Now which one usually we use? We use this mode over here. Usually we use this mode over here, which is 0, 1 with AVCC equal to 5 volts as our reference voltage. Okay, so 0, 0 if you want to choose any other reference voltage, 1, 1 if you want to use half of the AVCC, and if you want to use the AVCC, then you are going to use 0, 1. Okay, next is the AD max from 0 to 4, which is these 5 bits from 0 to 4. From 0 to 4 will give us these 5 bits. Now these 5 bits, if you look at them, you have the usual from 0 to 7. Then you have extra things. If you want ADC 0 with ADC 0 with a factor gain of 10, if you want to have a factor gain of 10, then you are going to use this mode. The second one is a differential mode. You subtract 1 from 0 multiplied by 10, then 0 multiplied by 200, then 1 minus 0 multiplied by 200, then port 2 multiplied by 10, port 3 minus port 2 multiplied by 10, port 2 multiplied by 200, port 3 minus port 2 multiplied by 200, and then we have differential inputs on all the pins starting from 0 minus 1, 1 minus 1, 2 minus 1, and so on until we get all the values. So we have different values. Usually we use these values, but if our signal is too weak, we can magnify it by using the gain over here and apply the gain for the circuit. So the analog voltage can be selected as 8 ADC pins, ADC 0, ADC 7 to ADC 0, and the differential input between two analog to digital converter pins. Again, factor of 1, 10 and 200 can be selected for differential inputs, and differential once more it's subtraction. Now how about this pin over here, or this bit over here, which is the left adjustment? Now your 10 bits can be either left adjusted or right adjusted. Now if you choose right adjusted, which is this one, or right aligned, which is this one, your most significant bits will be over here and you need to see them. Usually we use this mode when we are concerned and we want all the bits to be incorporated. Now if I only want the 8 most significant bits and I don't want these two, I can simply choose left adjustment and use them. Now remember, these two are the two most significant bits. They are not that important. Okay, so usually we can choose the higher, and that will be fine. So the digital output is stored in two 8-bit registers: the ADC, the analog to digital converter high, and the analog to digital converter low. The format of the analog to digital converter high and analog to digital converter low are interpreted differently depending on the flag of the analog to digital lift adjustment register. So it's important when retrieving the digital output, registers L must be read before registers H. Okay, you always read the lower before the higher. Next is the analog to digital converter control and status register. Okay, the analog to digital converter control and status register will give us a few things. First is the prescaler. Now, the prescaler, remember we said that we have two important things. The first one was the sampling frequency. The second was the quantization. And quantization, it's quite simple because we have already specified that we have 10 bits in the analog to digital converter. So the quantization is 2 to the power 10 is 1024 levels. This leaves us with the frequency. Now, in terms of frequency, we have the prescalers over here. And the prescalers will be using this. So the prescaler will divide the microprocessor frequency by a prescaler. You can either divide by 2, divide by 2, by 4, by 8, by 16, by 32, by 64, and by 128. This will give you some freedom because most of the time your analog to digital converter or your analog value is not changing that fast. So you don't want every 5 microseconds to read the value. You may want to read it every 4 milliseconds. So that's why we do the prescaler part to control how many samples we are going to take per second. These ADC interrupt enable to enable the interrupt. This is the interrupt flag. This is to enable the interrupt, and this is the interrupt flag. So this is 1 to enable the flag, and this is set 1 when the conversion is complete. This is for auto trigger. If you want to trigger the analog to digital converter by certain events. This is for start conversion, and this one is important. And this one is basically to enable the analog to digital converter unit, which is like a switch on for the whole system we are talking about. So this is basically the analog to digital converter control and status register A. Again, this is the prescaler. Now we have the special function input output register. In this side, the special function input output registers, we can find the sources of this auto trigger. If you choose to have an auto trigger for your analog to digital converter, then you should go and set the special function input output register. So the special function input output register, in the most significant 3 bits, we have a free running mode, we have an analog comparator can set the analog to digital converter, we have an external interrupt request, we have timer counter 0, compare match, we have timer counter 0 overflow, timer counter 1, and timer counter 1 capture event. These timers and counters I'm going to talk about in details inside our embedded system class inshallah next year, and the rest will be straightforward if you are using an analog comparator or an external request interrupt. Usually in this class we are going to set the external triggers to 0, but it's good to know that these things do exist in our system. Now, the steps to use the analog to digital converter. First of all, we need to configure the analog to digital converter using the analog to digital mux, the analog to digital control status register A, and the special function input output register. So, few questions we need to ask. What is the source of the analog to digital converter? What reference voltage is used? How is the outputs aligned, left or right? Enable or disable the auto trigger. Enable or disable the interrupt. What is the analog to digital converter prescaler? Then the next step is to start conversion, and the final step is to extract our output. So, for example, we want to perform an analog to digital converter for a sinusoidal signal and display the results on LEDs. So what is the analog to digital converter source? Okay, what is the reference voltage? Do you want left or right? Here we want left. The top 8 bits are only considered. Enable or disable the analog to digital converter auto trigger. Enable or disable the interrupt. What is the analog to digital converter prescaler? This is 2 for fast conversion. Now, this is filled in the analog to digital converter mux, as you can see over here. 1 is 0, 0, 0 because we are choosing ADC 1. Then left alignment, then 0 for reference. The reference voltage is 0, 1 because we are choosing the 5 volts. As for the control and status register, we have the prescalers set to 0, 1 because we are choosing a division of 2, and the rest are zeros, and we want to enable only the analog to digital converter. Then next we apply our C code. Our C code will look something like this. So DDR-B is equal to 0xFF, setting port B to zeros. ADC mux, we enabled the mux, we enabled the analog digital converter. Then we applied our values, and things will work immediately without any problems based on this. So basically this is our week's class, which is the end of microcontrollers for this course. Of course, again, this course will talking about microcontrollers and microprocessors, and this part is for microcontrollers. During the next 2 modules, we are going to talk about microprocessors. Basically, the last 2 modules will talk about microprocessors programming in detail, but for now, the rest of this module is basically divided for talking about microprocessors in total as an architecture, and how they are built, and how we can start programming microprocessors based on this. Hope you have gained some information from this tutorial, or sorry, from this class, and hope to see you all soon. Thank you for watching.